The potential energy of a two-charge system will be given by U equals KQ1Q2 over R. We find that if the two charges have the same sign, then the electric potential energy between them will be positive. And this tells us that it requires work to bring like charges together. However, if the charges have opposite signs, then the electric potential energy between them would be negative. This means it'll require work to separate the charges. It's a mathematical expression of what we had seen in the past. If there happen to be more than two charges, then we have to find the electric potential energy for every pair of charges and add them algebraically. And this sum can be thought of as the work required to bring the charges together from an infinite separation one at a time. In the Bohr model of a hydrogen atom, a single electron can only exist in certain allowed orbits, where the radius of each orbit is r equals n squared times 0.0529 nanometers. N can be any integer. According to the formula for the Bohr orbit, we'll plug in a 1 for n. And as we can see, this will give us 0.0529 nanometers. So let's start with that. Our proton and our electron are going to be separated by 0.0529 nanometers. Let's use the electric potential energy formula. KQ1Q2 over R. So we'll want 9e to the 9. Charge on a proton, charge on the electron. And then we'll divide by our allowed orbit radius. All right, I'm getting that the electric potential energy here is negative 4.36 times 10 to the minus 18 joules. And this is an important number because it tells us how much work is required to separate an electron from its proton. You could imagine yourself physically standing by the electron and wanting to push it all the way out to an R of infinity. Okay, so how much work would it take? 4.36 times 10 to the minus 18 joules. We can repeat the calculation for the second allowed orbit. This would be n equals 2. So we have the formula r equals n squared times 0.0529. Let's plug in our 2. All right, this is going to be a radius that's 4 times as large. So whereas we started off here at an n of 1, now we're going to have our electron way out here. at an R of 0.2116 nanometers, and this is n equals 2. It could be thought of as an electron which jumped from the first orbit to the second orbit, and it requires energy to do that. Let's do the calculation. Okay, now I'm getting negative 1.09 times 10 to the minus 18 joules. Let's just make sure that it makes sense. When charges have opposite signs, the potential energy can be thought of as the work required to separate the particles. So here, when the plus and minus are very close, it requires 4.36 times 10 to the minus 18 joules to pull that electron out to infinity. When we're located here, though, the negative is farther from the proton. And now it only requires 1.09 times 10 to the minus 18 joules. It's 1/4 of the work that would have been required to pull this electron out to infinity. Interesting. Finally, let's find the electric potential energy when the electron has totally escaped. Well, according to the numbers, it would be easy to solve. 0. The conventional electric potential energy at infinity is always 0.